Today I will start by recalling the dissection principle once again and one more remark that I forgot to make when I was covering that part. So I wanted to do it last time, but I forgot, so I'll do it this time. Let's quickly recall the setup. So suppose you have a Markov chain Xm on a state space S and transition matrix P. Now you fix a state I for the time being, and suppose that your Markov chain starts at I. In other words, the initial distribution is delta I. Then the 0th return time to I is defined to be 0. The first return time is the first time the Markov chain comes back to I. Of course, this can be infinite if the Markov chain never comes back to I. But on the event that this is finite, we define the second return time to be the second time the Markov chain returns to I. What it means is that first time, strictly after the first return time, when does the Markov chain return to I? Again, there is no guarantee that this will be finite, but if it is finite, then we'll define the third return time on that event, and so on. So continuing this way, on the event that the first n return times are finite, we defined the n plus 1th return time to I as the first time strictly after the nth return time to I, when the Markov chain again returns to I. Okay, this is the n plus 1th time the Markov chain returns to I. Then we define the sequence psi case as psi1 was the length of the first excursion, which was essentially just the first return time in this case, followed by the first excursion. So you start from x1 all the way up to the first time it returns to I. Of course, tau I1 can be infinite, and therefore this can be infinite, and this is an infinite sequence. However, if that is not the case, if the first return time is finite, then on that event, okay, on the event that the first return time is finite, then on that one you define psi2 to be the length of the second excursion, which is the difference between the second return time and the first return time, followed by the second excursion. Okay, this is the second excursion. Right? So continuing this way, on the event that first n return times to I are finite, define psi n plus 1 to be the length of the n plus 1th excursion followed by the n plus 1th excursion. Okay, so this is your psi n plus 1. When fixing an I in S, suppose m is a positive integer such that starting from I, the first m return times to I are finite with positive probability. Okay, this is an assumption, and then we defined pi hash to be the conditional probability of pi with respect to this event. Now this event has positive probability, so we can define the conditional probability. So this conditional probability was pi hash. The dissection principle stated that with respect to pi hash, psi1, psi2 up to psi m, which are all well defined, okay, because all of these under pi hash, all of these are finite with probability 1. So therefore, all of these are well defined. So not only that they are well defined, they are actually IID taking values in this space. This is a statement of dissection principle, and we actually proved it in the case m equal to 2, and then remarked that for other m it's just more notation. It's the same proof essentially. So the proof was long, but the idea of the proof was repeatedly use Markov property essentially. And the result is also expected, and it's basically Markov property manifestation of that with respect to excursions. okay, in terms of excursions. So now you start from I and you look at the returns to I. These are all IID. Now the question is, suppose instead of starting the Markov chain at I, you start it at some j which is not equal to I. Then what happens? In this case, what we will do is we'll still have this assumption, okay, that this is positive. This probability is positive. Okay, so there's a small catch here. So we'll have the assumption that this is positive starting from J. Okay? And we'll define the conditional probability to be the probability. We'll define the probability P star J to be the conditional probability of Pj with respect to conditioning on this event. Now, if this event has positive probability under Pj, then only we can do that. So let's assume that this conditional probability is well defined. In that case, what we can show in a similar fashion, we start from a state J and then we come back to I. We don't come back to J, right? We come back to I. And then again, we come back to I over and over again. So our first excursion is essentially starting from J, but first time you return to I. But the second one is starting from I and then returning to I. Third one is also starting from I and then returning to I. So therefore, Xi2, Xi3, these are all IID. Because once you are back at I, it's the same dissection principle that will hold. So under this measure, P star J, let's assume that this measure is well defined. Okay? Under this probability, P star J, let's assume that this probability is well defined. The E-valued random variables, Xi2 up to Xim, these are IID. However, Xi1 is independent of Xi2 to Xim, but it may not be identically distributed with these guys. That's expected because the first excursion in this case is different. You start from a different state J and then come back to I. Second onwards, all of them are you're starting at I and then coming back to I, and therefore all the excursions are IID, and so are the Xi-i's. So this we are not going to prove, but it can be shown in a similar using a similar argument. But this might be useful sometimes. That's why I wanted to state it. So it just states that if you start but in a different state J and then look at the returns to I, then second onwards, all the excursions are going to be IID. But the first one is going to be independent of the other excursions, but it may not be identically distributed with other ones. That's what this is saying. Now here I have defined this without saying that this probability is positive under Pj. Just assume that this is well defined. Okay, so with that remark, I would also like to go back to the exercise. So last time there was a mistake in the exercise and we corrected it. I sent you an email about it and then we also discussed it in the discussion session. Now this exercise also, in light of this remark here, can be modified slightly. So instead of looking at one state I, look at two states I and J. Now I ask you to show that for all positive integers k and l, and for all I1, I2 up to IL states in S, this probability starting from J, but we are looking at return to I, okay? So whatever happens after the first return to I is independent of the first return to I, and after you start return to I for the first time, you're starting afresh from I. So that's what this exercise tells you. So under Pj, this probability is the probability under Pj of first return time equals k, and then the probability that once your first return time is k, that means at k, you're already at I, so at k plus 1, so you should start from I. And then by stationarity, you'll just start afresh. So this is the form, this is the exercise that we'll be needing today. It's slightly more general than before. Last time I gave you this exercise. Well, I corrected it. Initially, there was a mistake, but I corrected it. So when I gave this exercise, it was the case I equal to j. But not necessarily I should be equal to j. You start from any j, look at the first return to I, and then what happens afterwards. What happens afterwards is going to be independent of the first return, whenever it is finite, of course. And then once you return for first time to I, you are starting afresh. Of course, this is just Markov property. Okay. And then I ask you to prove it using the definition of Markov chain, which is MC. Okay. We'll be using, as I said, this exercise today in one of the proofs.